Okay, so let's get started. Today we are going to start a new topic, which is going to be cloud computing. We will make the connection to all the discussion we had on virtualization so far and see how it is applied in both data centers and cloud computing. And then in the part 3 of the class, I'll talk about Kubernetes and orchestration and how that relates to both data centers, cloud computing, and also container virtualization. Uh, so that's the agenda for the day. What I wanted to also announce was roughly where we are in the class, right? So lab 1 is done, right? It was due earlier in the week. We will hand out another lab sometime this week. It's going to be due in early April, right? It's after the spring break. So just keep that in mind. You have 3 weeks. So even if you are not here for spring break, you have some time to work on it. But the other thing you want to keep in mind is the week after spring break is our midterm exam, right? So there'll be a midterm, and maybe a few days after the midterm will be the lab. So just use your time well. We have given it out several weeks in advance, so you can get started early and not have time pressure at night. So one of the things that always happens, no matter how early we give the assignment, is people start late and then you run out of time. You always wish you had more time and so on. So I just wanted to tell all of you that we will give you these labs fairly early, but it's up to you to use your time well and not put everything off till the last week. Then you have to deal with an exam and a midterm exam and a lab due more or less at similar times. Okay, so keep that in mind. But we'll continue our discussion on these issues. So today is cloud computing, and then I think we are going to switch gears and start talking about other topics. So this is kind of the last of the topics that relate to virtualization. So we'll start with data centers. I'm going to explain to you what they are, and we'll talk about cloud and Kubernetes. So what is a data center? Think of a data center as a facility that is used to house and run very large number of servers. Okay? So there are applications that may need lots and lots of servers. The facility that you actually house them, okay, they are referred to as data centers. They're also called server farms or storage farms. Depending on the size of the data centers, they come in many different sizes. You may have thousands of servers or hundreds of thousands of servers, depending on the size of it. Okay? And the storage that you can see in these data centers can run in petabyte. Okay? So what are they used for? So they are very common in companies of all sorts. The data centers are the one place where they have their servers. So that's the servers are what are used for running all kinds of server applications that you need for an enterprise. Okay? So for example, even a university is an enterprise, and the university data centers will house applications like you have Spire, right, for doing registrations, and you have Canvas for learning management. So these kinds of applications typically are run in data centers. So that's the enterprise use case. Internet companies use them at very large scale. This is companies like Google and Facebook and Microsoft. They have all kinds of services they offer. The Google Mail and Google Docs and YouTube and social media applications. Those also run on lots of servers in data centers. And we'll talk about cloud computing today. There's a third use case. So cloud computing platforms run on data centers and offer these resources to end users and end customers. Okay, so, and the types of workloads that run on data centers range from data processing workloads to online services that are web-based to all kinds of business applications. So let me show you a picture. So here is a picture of one aisle of a data center. Right? So the way the mental model of what you should have in mind is you've been to a supermarket, right? So the way a supermarket is laid out, it has aisles and there are shelves, and shelves have grocery items or food items. Okay? You should think of a large supermarket-like facility, but usually even larger, that have aisles. Okay? And the aisles in this case are actually going to host servers, right? So here's an example of an aisle, okay, in this large facility, and you will see that there are racks of servers, right? So, and there will be many such aisles. Each of them will have its own set of servers and so on. And then there are many aisles. So these are very large facilities. So it's a giant warehouse or a facility that's filled with racks of servers, storage arrays, and so on. Okay, and to build a data center, you not only need to have power infrastructure to power all these servers. The servers are going to consume a lot of electricity, okay, in the aggregate, especially if those servers have GPUs on them. GPUs are very energy intensive, so the servers consume a lot of electricity. But in addition to doing that, the servers also generate heat. Okay, so any machine, if you have a laptop, if you're doing computation and you touch its underside, you'll see that it's running warm because it's generating heat as it computes. Servers are not going to be any different, so they generate a lot of heat, which means that they need a cooling infrastructure, a very large cooling infrastructure to cool all of those servers so that they don't overheat. Okay, so in addition to the compute and storage infrastructure that you will see in a data center, you will also have a cooling infrastructure. You will have a power infrastructure to power these servers, and you might have backup generators if there's a power outage from the grid. You might want to use backup power to keep all the servers up and running. Okay, so needless to say, it's very expensive to build these data centers. Okay, later on we will have some more lectures where we will get into what is the energy consumption, how do you make them energy efficient, and so on. But that is something we will defer to a lecture where we talk about energy aspects of distributed systems and data centers. So today I'm not going to get into this material, but I just want you to know that the electricity bills that this data center generates can be in millions of dollars, right? Unlike your home electricity bill might be $100 or something, but these consume so much power that it costs a lot of money to just power these data centers. So they are expensive to build, they're expensive to run as well. Okay. Now, data centers have been around for a long time because there have been servers that have been running business applications and other applications for many decades. Okay, but they have changed in how they have been designed over the years. The more traditional model for data centers was what is called a static model, where there are physical servers. You basically deploy applications on the servers, and the system administrators manually manage which application is running on which servers, how much storage to allocate to them. This is all handled by a group of human system administrators that are monitoring needs, and as needs change, they can change the allocations and so on. Okay? So that is how data centers were designed and built for many decades until virtualization technology came along. And that made things much easier. And I'll show you some pictures in the next few slides. So now, rather than running applications on physical servers, these physical servers will run a hypervisor, typically a type 1 hypervisor, which I already talked to you. Okay? And you then have virtual machines that are built on these servers, and applications run inside virtual machines. Okay? This makes it much more flexible to map applications to servers, because if, let's say, a server gets overloaded, you can migrate or live migrate that VM to some other server that's not using all of its resources. So now the mapping of applications to server no longer needs to be static. You can resize the virtual machine. You can move it if the server gets overloaded and so on, which allows for a lot more flexibility. Okay? All this is a way to say modern data centers use virtualization technology quite extensively. In fact, virtualization is at the heart of all of these data centers. And here are some pictures to show you all of these things. So there are two use cases I'm going to talk about. So here is a rack of servers. I just showed you a data center. I said there are many aisles. Aisles have racks. Here's a rack. Rack is basically a stack of servers. That's one of them. Okay? That blue thing that's on top of that server is essentially a hypervisor. Okay? So the server is running hypervisor, and you'll see that there are six virtual machines that are running on this server. Okay? Each virtual machine has its own OS, okay? And then it runs some application. Okay? So this is essentially, each of these virtual machine is a virtual server, okay, from a outside it just looks like a server. You can log into it, you can restart it and so on, except that it is running as a virtual machine on a physical server. Okay? So this allows us to do various things. What is shown here is essentially consolidating a set of applications onto one server. So rather than running this application on separate servers, you made a slice of a server, which is now a virtual server. That slice is a virtual machine. That virtual machine has some fraction of the resources on that physical server allocated to it, some number of cores, some amount of disks, some amount of memory. Okay? And then you ran an OS in there, you run an application. So now you could pack 6 of these servers onto one physical server. Okay? So rather than having 6 different servers, you can have one bigger server and build 6 smaller virtual servers and then run your applications. Right? So this makes things more efficient. It is faster to deploy because you are using virtual machines to deploy. It's easier to maintain because you can move them around and so on, which I'll show you as well. Okay? That's one use case of virtual servers. But then there's the other use case which we also talked about, which are virtual desktops. Okay? So what happens in virtual desktops is I already showed you type 2 hypervisors. Right? These are hypervisors that you will run on your laptop. Okay? Multipass is an example, and last time I showed you parallels and so on, and you can run an OS in them and applications in them. Okay? Now imagine that rather than running this on your laptop, you actually have a server that is running virtual machines. Okay? And then the server runs a desktop operating system. It doesn't run a server operating system, and it runs essentially somebody's applications in it. And so rather than having your PC data and computations on your machine, you are actually going to have your machine connect to a server somewhere. Okay? Then that server is running a full-fledged PC-like environment, okay, which is really a virtual machine and application in them. So you connect to it and you do all your compute that. Okay? So what this means is now your data, your applications are not on your local machine. They are actually on the server there. The local machine is simply connecting to that server, okay, and doing all of the compute remotely. Okay? And you can have a graphical environment. You don't have to SSH in it. Of course, you can. But this is just you have a full-fledged graphical environment. You can connect to it and so on. So in this example, you see that there's a user at work. Okay? You see here that there is no PC that is shown. There's a monitor and a keyboard because you're literally connecting to a PC in a remote server and doing all the computations there. You can go home and you can use another machine. In this case, let's say it's a home laptop. But rather than running the applications actually on the laptop, you are connecting to a data center server and then doing your compute. Okay? So these are called virtual desktops. Okay? There are many scenarios where this is actually preferred than letting users run applications locally. So for examples, you might go to a supermarket checkout counter. Right? That checkout counter, when you are scanning your items, there is a computer that's scanning. Often that computer is actually not a PC running locally, but it could be a VM running somewhere else. And that computer that's doing the scanning is simply connected somewhere else, and all the billing is that is showing you is the app that's running somewhere in a cloud data center. Okay? So these are some examples of what you can do with a data center. So you can have servers, applications, you have virtual desktop applications, and so on. Is this clear? Any questions here? Okay. So now I'm going to show you what we talked about last time, but more in a data center context as to how you can use things like live migration and things of this sort. So I already said a server can be sliced into multiple virtual machines. So let's, for example, now take 2 physical servers, not virtualized. Right? So this is a Windows machine. That's a Linux machine. So that's an orange application that's running on Windows. Blue application is running on VM. Okay? Now, this is normal servers, no virtualization. Right? Now, let's assume that there is a server there that's on top, that's running a type 1 hypervisor, and you wanted to run these applications using virtualization. So what is going to happen is you will not run them on a physical server. You will construct now 2 virtual machines. Right? One virtual machine will run Windows. Okay, that's VM1, and you run the orange application in there. The second virtual machine is running Linux. You run another application in it. Right? So now you are running those applications on a single server, in this case, using virtualization. Okay? That should be clear as to how this works. But now what does this give us? Why would we have not done what we had previously? Okay? So here's something you can think about, right? So let's say the load on the Windows machine has grown. Okay? If you had run this on a physical server that I had shown you previously, that server gets overloaded, right? And then you cannot actually run that application anymore because the load on the machine is too high. Okay? Now, in this case, also the VM has become overloaded because you have essentially grown the load inside one of the virtual machines. But because this is now a virtual environment, you could do things that you could not do with physical machine. In particular, if there's another server in the data center, okay, I could live migrate that VM to this data center. Sorry, to that server, right? So that VM that was running here has moved here. I could just migrate it. Now I freed up resources on the first server. Okay, so now I can run that virtual machine because it has now more resources to use that it did not have previously. Okay, now this can be done fairly simply because I just explained in the previous class how you can live migrate a virtual machine with no downtime. But if you had physical servers and you wanted to do this, you would have to go buy an extra server. Okay, then you would have to physically copy all of that data, move it, recreate it, and so on. So human administrator has to perform this task, which takes much longer. Right? Here you can rapidly do this in matter of minutes, but with physical servers it might take hours, or if you do not have a server, first you got to go buy it and so on. But let's assume if everyone had a server, it would take someone hours or days to do this. Here you can do it in minutes. So virtualization has allowed us to adjust the allocations of virtual machines as they change. I can give that VM more resources or less resources. I can move VMs around using migration and so on. So this is a level of flexibility that allows administrators to do things in a much more simpler fashion. So it is advantageous. In fact, there is a third layer that is called an orchestration layer, which we'll talk about, that can even automate this process. So human administrator doesn't even have to do this. That monitoring software will figure out one of the VMs is overloaded. It will automatically migrate one of the VMs to another machine to free up resources. So you can even automate this entire process so that it's done without any human intervention at all. Okay? So these are all advantages you do not get if you did not have a virtualization layer running on top of this server. So this is why all of the data center servers are virtualized. And you can use this additional flexibility as a result of all of this. Any questions here? Is this clear what I said? Okay, so there are many of these technologies I already showed you last time. In type 2, you have things like Parallels and VirtualBox and Zen. VMware actually builds both type 1 and type 2 hypervisor. Linux has KVM, which is kind of a type 1 hypervisor. So you can do this in Linux without buying any software at all if you wanted. Okay, so let me now give you some idea of how you can think about data centers and costs and efficiency and so on. I already explained to you that running a data center is expensive because you have lots of servers. First of all, those servers cost money, right? If there are GPUs in them, they also cost money. But once you bought the servers, running the servers also is expensive because they consume a lot of electricity, right? And then I said you have to then cool the servers, which is additional cost because you have to run ACs to actually cool the servers. That also consumes electricity, right? So there is a way to decide how efficient your data center is, right? So I'm going to show you two ways you look at it. One is you can simply look at, this is a pie chart that telling you for a hypothetical data center, what is a monthly cost. Okay? It's just an example. And you will see that the green part is the electricity cost. The red part is the power, okay, so infrastructure cost. And then the blue is essentially amortized server cost of buying. If you, let's say, you buy the server and amortize it over a 3-year period, that's the cost. So you will see that there are significant costs that you will incur. So it's all numbers that are in the millions of dollars. This is a small data center. Okay? Larger data center, there's just hundreds of millions or billions of dollars. But this just example tells you that cooling and electricity and power costs are substantial. Okay? So the metric that is often used to measure how efficient a data center is called PUE, okay? Power usage effectiveness. Okay? That metric is simply a ratio. Okay? It's the ratio of the total power consumed by the data center over the server power, or the what's called IT power, but it's really server plus switch power. Okay? So if you think about it, what is the total power consumption of a data center? It will be power used in cooling, all the ACs and maybe all these extra lighting and things of that sort. And then the power used to actually power the server itself, electricity used to power the server. Right? So the numerator is everything. Think of it as the total bill that the data center pays every month. That's all of the electricity in this case. Okay? The denominator is the electricity consumed by the servers plus network switches. We ignore the network switches, just the servers. Okay? So that's the ratio. That ratio tells you how efficient your data center is. Typical ratios for PUE run at somewhere between 1.7 to 2. Okay? So what that means is for every unit of electricity that the server consumes, there's 0.7 units of electricity used to cool the servers for everything else the data center needs. Okay? So 70% extra has to be put in just to run that server. Right? Now, clearly, the closer you get to 1, you'll see that it's more efficient the data center is, because for every unit of electricity, the extra power you use for everything else that you need to do in the data center is small. That means your data center is more efficient. All of the power is actually going into the servers, which are the ones doing the work. Right? So there are companies like Google and Meta and Microsoft that have tried to optimize this by building more and more efficient data centers, and their numbers are getting closer to 1.1, 1.05, and so on, which means there's a 10% overhead or 5% overhead. So they are very, very efficient. Okay? The way they do this is that they've optimized the cooling infrastructure. For example, rather than running ACs, they use something like free air cooling. You can put the data center in a cold climate and then just pull outside cold air to cool the data center, rather than cooling it using air conditioner. Right? So that's much cheaper than actually having an AC doing the work, for example. Right? You can do that for many months of the year. You are essentially getting less expensive ways to cool your servers and reducing your electricity cost and running things more efficiently. So all kinds of interesting optimizations to make this more efficient. Okay? But the only thing you really need to know is the efficiency metric is called PUE, is total power over the IT power or the server power. Okay? And the closer that ratio is to 1, 1 is ideal. Right? No one can do 1 because that says that there is no cooling needed, there's no extra thing needed. But the closer you go to 1, the more efficient you are. Okay? Typical data centers are in the 1.7 to 2 range because they are not super efficient in that regard. They do have extra power they consume to run the air conditioners and so on. But the most efficient ones are running closer to 1 these days. Okay? Any questions on this? Right. There are lots of interesting ways by which you can optimize the PUE of a data center, which I will not talk about in this class. Okay? But there is papers that you can go and look at that tell you how to make this infrastructure more efficient. Lots of interesting things, like Microsoft, for example, built a data center that they submerged in the ocean, and they're using ocean water to cool the data center. Okay? All kinds of stuff that you might think is somewhat crazy, but people have tried to use it to make these data centers run more efficiently. Okay, so with that background, I'm going to now switch gears and talk about cloud computing. Okay? We'll talk about different flavors of cloud computing, what they are used for, okay, and so on. Okay? So first of all, what is it? Right? What do we mean by cloud computing? So I have a very basic definition which says it's the use of remote servers to run distributed applications. Okay? That's the basic concept. That is not enough by itself. So cloud computing essentially means that your applications you want to run, you run them on remote servers. Okay? Now, of course, you can run your application can run on an EdLab server. That doesn't mean you're using cloud computing. The other thing that goes with cloud computing is that there's a charging model associated with cloud computing where you don't own the machines. You're renting the machines or the resources. Right? So there will be a pay-as-you-go model which says how much resources did you use, and you get charged based on that. Right? So mainly the cloud computing model switches the way you actually use servers from having to buy them to having to lease them or rent them. Okay? So, and that's what we are going to see. So essentially, a cloud computing platform at its heart is just a data center, but that this data center is owned by the cloud provider that is selling resources to any user or a company. Any company can go and say, I want to rent 100 servers or 5 servers or just one server. And I want to rent them for a day or 1 year. You can specify your requirements. The cloud provider will create one or more virtual machines to meet your needs and allocate them, or storage to meet your needs or allocate them. So there's no need to create or deploy your own data centers in this case, because you can go and rent them very easily. Okay? So it's much less expensive for small as well as large companies to go and buy resources they need on the fly, rather than buying servers and then deploying them in their own data centers. I already told you it's expensive to build them. Okay? So the benefits, and we'll see some details of all of this in the next few slides. So the benefits of this is that you can access these servers from anywhere on the internet. It's a billing model that uses pay as you go. You pay for the amount of resources you need. It's highly scalable. You can obtain resources on demand. If your needs change, you can say, I need another one server or another 100 servers, and they're ready within minutes, which is very useful. And if you don't need them, you can say, I'm done. You hand them back, and they will be stopped. You will not be billed for them anymore. So you can acquire and release servers, storage resources on the go, okay, and only pay for what you're using, rather than having to buy a lot of servers and they're sitting there idle because you don't have applications to run on them. Okay? So it's shared in the sense that the cloud provider in this case is selling server capacity to lots of different customers, right? So there are many customers, which could be companies or single user developers that have leased capacity, and they're all using servers in a data center. So they're sharing the resources that are present in a data center. But from the cloud provider standpoint, they build these gigantic data centers. They have economies of scale, so they can afford to lease these resources for a much lower price than if you are to build your own. Okay? So that's the advantage of doing it this way. But now let's get into some of the details of how cloud computing works. So as I said, you are essentially in a cloud model trying to rent resources, okay, from a cloud provider. There are many cloud providers. Amazon runs a very large cloud platform. Google runs a Google Compute Cloud platform. If you heard Microsoft Azure, Azure is Microsoft Cloud platform, and there are several more, right? There's Oracle and Alibaba, and so many companies run these cloud platforms. But then question is, what is it that you actually get from this cloud platform when you as a user or a customer want to get resources from the cloud? Okay? So cloud resources come in different flavors, and this slide talks about 3 very important ways you can lease capacity or resources from the cloud. Okay? Depending on what you are getting when you ask the cloud provider for resources, you can have what is called an infrastructure as a service, or IaaS is the acronym. IaaS cloud. You can get a platform as a service, or what's called PaaS or PaaS cloud, or you can get software as a service, or what's called SaaS cloud. Okay? These are essentially 3 flavors of cloud platforms. Okay? So how are they different? What is different across them is what is the core block of resource that you actually get from the cloud provider. So at an infrastructure as a service cloud, you go to the cloud provider and ask for servers and disk space. Okay? So you will get a virtual machine, you will get disk, and then you as the owner of, not owner, but the user of that virtual machine can deploy whatever you want in there. You can deploy whatever VM OS you want, whatever application you want. So essentially, this is the bare bones. You just go and say, give me some number of servers. And then the cloud providers say, here they are. You can then run whatever application and OS you want inside those servers. Okay? And then you have to manage those servers like you manage anything else. Right? So this is essentially raw infrastructure. So it's called that is why it's called infrastructure as a service cloud. Okay? One level up is called a platform as a service cloud. So in this case, you do not go and ask for individual servers. What you do is you say, I have an application. Okay? I built this new Java application or I built this new Python application, and you say, deploy this application for me, right? And then essentially the cloud provider will take that code and they will develop it, they will deploy it on their platform. They might have a Java platform they built, they will take your Java code and deploy it there, right? You are not asking for servers. You are just telling them, here's my code, deploy it on your platform. It will run Java code or Python code, or lots of different languages are supported. Now, in this case, you are going to be billed by the number of users that are accessing your application. Okay? So they will monitor, saying you got 100,000 requests last month. I will charge you a penny or some fraction of a penny per request. So your bill is going to be this much. And the cloud provider will take care of figuring out how much servers to allocate to your application. You as a developer no longer have to figure out, should I buy a small server from the cloud, a big server from the cloud? You don't deal with that. You just say, here's some code, deploy it, and the cloud platform will figure out based on the workload where to run it. Should it be run on a big server, small server? They figure it out. You are just paying by usage, okay? Not by how big the server is. In the previous case, you as the cloud customer actually have to ask for a server of a certain size. The cloud platform might have 10 different configurations. You can say, I want a server that has 4 cores and so much RAM, or I want a server with a GPU in it. You have to specify what you want, and they'll give you exactly that type of server, and you pay for that server often by the minute or by the hour, depending on how many minutes you use or hours you use. Okay? If the server is too big, okay, your application doesn't get enough workload, you are still paying for that server. It will have unused capacity. If it's too small because you got a lot of workload, then you have to go and get a bigger server and move your application. Okay, so that's what you will have to do. The platform as a service cloud, you just don't worry about it. They will handle scalability as the cloud provider will handle scalability for you. You are deploying applications on a platform. That's what they give you a platform, you deploy application, the cloud provider manages everything for you. Okay? And then you have software as a service cloud. So here you have essentially a cloud that has pre-packaged applications. And then you as a customer, you basically say, I want to get this application for so many users in my organization or as a single user. So example of this is things like Gmail. Okay? Google Mail is a software as a service for mail application. Right? So as an organization like UMass, we'll go to Google and say, there are 20,000 students at UMass. We need Gmail service for 20,000 users. Okay? And then Google will say, okay, each user you will pay so much. And then so this is your monthly bill. They take care of the application code. They take care of figuring out how much this or what types of servers to run. So it's one level above where you don't even develop the application. The application is pre-packaged and you are just, it's hosted by a cloud provider in this case, right? So our Canvas, which you access, is also a cloud application. Okay, it's not running on UMass server, it's running on somebody's cloud server. In fact, the company that developed Canvas offers a cloud service. So you just go and say, we need this learning management system for these many students at the university, and then they're paying based on it. Okay? So different layers of the stack. Okay, here you are essentially renting hardware, really renting virtual machines that run on hardware, but it's almost like renting hardware. Here you are renting hardware plus a software that is allows you to run applications. Okay, that's configured by the cloud provider. Here you are renting entire applications. Okay, so these are the layers you have to really keep in mind. As far as this class is concerned, you will actually be using infrastructure cloud. You will deploy some of your lab code onto a cloud platform in the next lab or two. Okay, so you will get some flavor of what it means to actually get a cloud server and how to deploy code and so on. Okay, here's an example now of an infrastructure as a service cloud. This is an example for Amazon's IaaS cloud. It's called Elastic Compute Cloud, or EC2. Okay, so Amazon's cloud that offers you the servers is called EC2. Okay, it rents servers and storage to customers. Okay, and uses virtualization to share these servers. So they have large servers, they carve it up into virtual machines of many different sizes and rent out this virtual machine. Okay, so here is an example. It's really a toy example at this point because Amazon's EC2 clouds has hundreds of configurations. It's showing 3. right? So here it says you can get servers in 3 sizes: a small, a medium server, a large server. The small server has 1 core, the medium server has 5 cores, the large server has 33.5 core. I don't know why there's a half, but that's what they did at one point. Okay, and then this is the amount of RAM associated with it, and they give you a price. Okay, you say this one costs 2 cents an hour to rent. Okay, this one costs 17 cents an hour, and that costs $2.10 an hour. Okay, and it comes with some amount of storage, and then if you need more, you have to pay by the gigabyte, and it is also some amount of bandwidth cost. Okay, so you can get a server, and if you run it for just 1 hour and say I'm done, you will pay 2 cents because that's their charging. So they actually charge you at a very fine grained level. Or if you use it for a month, you'll basically pay a few dollars for that month. Right? So that's how they are going to bill based on what you ask. And then you can simply go and request these servers saying, I want 1 or 10 of them or 100 of them, and they will provision them very quickly. In a matter of minutes, all your servers will be ready, and then you can log in to them and do whatever you need to do, and then they'll charge you accordingly. Okay? That's an example of how you actually use infrastructure as a service cloud to deploy application. Okay? And the virtual servers, you can deploy any OS you want. And you can say, it needs to run Linux, or it needs to run Windows. They even have Mac OS as one of the offerings, for example. Yeah. Okay. So now there are actually many different flavors of servers you can get. I just mentioned that you can get small, medium, large servers, but depending on what kind of charging or what kind of commitment you want to make, you can also basically get these servers, those same server configurations in different flavors. The default one is called on demand. Okay? On demand says, as a cloud customer, you can request these servers at any time. They will be created for you on demand or on the fly. You can keep them for as little or as long as you want. You terminate the server whenever you're done. Okay? That's the basic model. You pay by the minute. You provision on the fly. You pay by the minute. You keep them until terminated. And there is a billing model. I already showed you that was for the on-demand billing model. Okay? But suppose you want the servers for a long period of time. So I want it for 3 years, okay? Not 1 minute or 5 minutes. Okay? So in that case, you can get these same servers at a discounted rate. Okay? These are called reserved instances. Reserved instances require you to make longer term commitment. Okay? The minimum commitment is 1 year. Okay? So you can say, I want the server for 1 year. I want the server for 3 years. In this case, you are going to get the same server, but because you have committed for a longer period, you will get the same server at a lower price. Okay? On demand, as there's no commitment, there's no contract or anything. You can keep them for as little or as long as you want. But if you have the ability to make a longer term commitment, you get it for lower price, a discounted price, because that way this cloud provider knows that they can have you as a customer for a longer period. So if you need servers for longer, reserved instances are the way you are going to actually go. Okay? And then there is something called spot instances. Okay? Spot instances are a way for the cloud provider to sell excess capacity that's unused, sitting idle in their cloud data centers at highly discounted prices. Okay? So what they do is, let's say the cloud data center is 50% utilized at some point. Okay? So 50% of the capacity or servers are sitting there idle. Okay? So they are not making any money because nobody has used those servers. Okay? So what they do is they take this excess capacity and then they say, here is a highly discounted price. I'll give it to you as 1/10 the price of a on-demand server. Right? So you got 90% discount or 70% discount. Okay? So you can go and say, I will take a spot server because it's more cheaper than on demand. Okay? And then you will get that. So if the server is available, you are going to get it at a much lower price than an on-demand server. Okay? But there's one caveat when you have a spot instance, which is that the server can be revoked, taken back by the cloud provider. Okay? If the demand comes back, they can say that I need the server back because I actually have regular customer. So it's essentially you're renting idle capacity for as long as the capacity is idle. When the demand comes back, they have the ability to take it back. Okay? This is not the case for on-demand and reserved. Once you get the server, it's up to you as a cloud customer to keep it for as long as you need and then return it. Okay? The cloud provider doesn't come and say, I'm going to take it back. But in spot instances, they are going to give it to you at a much cheaper price, but they have the ability to pull it. Doesn't mean they will always take it back, right? Maybe your job is done. If you have a 6-hour machine learning training job, you get spot servers, you run for 6 hours, and then you're done and you got the same work done at a much cheaper price. But if somewhere in the middle that there's demand for on-demand servers from regular customers, they will the cloud provider will send you a warning saying, okay, the server is going to be revoked, and then pull the server back. So in this case, the application has to make sure it can save its state and resume computation at some other time. Otherwise, you lost all your work, right? So you don't run web services on spot servers. Obviously, it should be clear because the server disappears, a website goes down. So this is good for running batch jobs, things like ML training, simulations where you can actually pause and restart later and things of that sort, right? So it is useful for certain types of workloads, and you can then get the work done for a much, much cheaper price. Yeah. All right. So those are spot instances. So you have these 3 flavors of servers you can get. So as you can see, there are all these permutations that you got to think about. Okay. So next up is platform as a service cloud. Okay. So as I already said, in this case, cloud resources are offered as a highly scalable runtime platform. Okay. As a cloud developer of cloud applications, you are not now asking for servers like you did previously. Okay. You just bring your applications, you develop your code, and then you go and deploy this code on the platform. The cloud platform will figure out how much resources to provision. So in the back end, they'll say, should it run on a small server, medium server? You don't see any of that. You just see that you deployed your code, and maybe it's a web service, it's getting requests, and then it will figure it out. And moreover, it can do auto scale the application. If the workload goes up, the cloud provider is responsible for moving that application to a bigger server because they are charging you by the request, right? The application gets overloaded and requests don't get serviced, they are losing money because they could have serviced that request and charged you for it. So it is in the cloud provider's interest to make sure the application gets whatever resources it needs so that it can service the workload, and then they can bill you for it. They are charging you literally by the request. Every request that your application services will cost a small amount of money. They will add up all the requests that were serviced, and then you have to pay according to that. As opposed to saying, I rented 5 hours of the server. In this case, you say my request, the code serviced, the application serviced 10,000 requests. So that's how they're billing you. Right? So all kinds of languages are supported. So you can bring a Python application, Java application, Node.js applications, .NET applications. Just deploy it, not have to worry about getting servers or anything like that. Right? So as a developer, it's simpler, right? So as opposed to getting your own servers and deploying it, and you don't need to manage your own servers. Billing is based on workloads, and I'll talk about a model called serverless computing, which really looks like a platform as a service cloud. Okay? But this is basically what it is. Any questions on this? Okay. So there's a new model for deploying applications in a platform as a service cloud, which is called serverless computing. Okay. It's very similar to platform as a service cloud. So what happens in this case is developer deploys code on a platform, eliminates the need to provision servers. The cloud platform essentially has a platform where each server can, each application rather, can be scaled up or down based on the workload that's seen. And if there's no workload, you can even scale it down to 0. Whenever requests come, you scale it up. Okay? So in this sense, there's no difference between serverless computing and platform as a service cloud, okay, so far. Okay? But the main difference comes in how you write the application. Okay? The platform as a service cloud, you can bring any Java application or any Python application, and they will give you a way to deploy it. Okay? In a serverless computing environment, you have to actually deploy your application using a model, or you have to write your application code using a model that's called function as a service. Okay? In other words, you make your application highly modular, and you are literally writing individual methods or functions and then deploying a set of functions. Okay? As a request comes in, your serverless platform will invoke a function okay, and hand it the request. The function services that request and generates a response. Okay. Now, because your application might have multiple functions, not just one, okay, you can chain these functions together. Okay. So you can write your application as a set of 3 functions which say, okay, requests come, you invoke the first function. For the that function can then invoke another function, and then that can invoke some more function, and then responses are generated and so on. Okay. So you write your code as a very modular set of functions. Functions could be individual. If it's a small application, just one function is enough. Okay. If it's a bigger application, you write a bunch of these functions and you chain them together, and then you're essentially going to invoke these functions, and then the functions can invoke other functions. Okay. The functions are typically stateless, which means that if you have state, you have to put it into databases and so on, because the code may not run. You don't actually want to assume that I can keep code in memory variables and so on, because they can simply delete the application completely if there's no workload. Okay. So typically, you do not put any state in the code of the function. You typically keep all the state on disk or in a database. Okay. So you have to write the function in a stateless form and then deploy your code. Okay. If you write your code this way, you are using the serverless computing model. This is the most modern way you write code for a platform as a service cloud using a serverless framework. Okay. So you will essentially put it in this format, right? So you have to modularize it. Think of how do you have this function, they call each other and so on. Okay. At a very high level, if you think about it, those functions are kind of like similar to remote procedure calls. Remember, we talked about RPCs and RMIs. You should think about this as the flexible way to deploy RPC-like code in the cloud, except that each RPC is now a separate block. You don't have one big application with 10 RPCs. You write them in separate things and then chain them together. Each RPC makes another RPC call in another process and so on. So it's that type of model, but now in the cloud format. Right? Amazon has something called AWS Lambda that essentially allows you to deploy this. Okay? This is also, as you will see when we talk about web application, we'll talk about microservices. So microservices are also a way to build web applications using tiny services. Okay? They start resembling functions, but functions are even more fine-grained than microservices. They're even smaller snippets of code that you can write. Okay? So this is actually a very modern way of writing cloud applications if you want to use platform as a service cloud. Okay? So I'll point you to a paper that describes this in a little more detail where you can understand this better. Okay? We are not going to use serverless computing in any of the labs, so this is the only time you'll actually see it. Okay? So the last thing I want to say here as far as cloud is concerned is 3 types of cloud platforms. One is called public cloud, one is called private cloud, one is called hybrid cloud. Whatever I've been talking about so far is what is referred to as a public cloud. Public cloud essentially means that the cloud provider, in this case, these are large companies like Amazon, Microsoft, Google that run these cloud services, and they're open to the public. Okay? Any user, any company can go create an account on that cloud platform and start requesting servers. Okay? And then you just have to have a way for them to bill you and pay for it. Okay? So as an individual user, you can go to Amazon's EC2 cloud and then ask for servers. And in fact, as part of the lab, you will actually do that. Okay? So now, not all enterprises, companies are comfortable with saying, let's just go to Amazon, get some servers, put all of our data on Amazon servers and so on, because the data might be confidential, it may be private. So you just don't want to go and put it on third-party cloud server. Okay? So in this case, okay, what they do is they build their own cloud, which they call a private cloud. Okay? So private cloud is essentially has all of the features, functionality I talked about, but it is a cloud that deployed for a single enterprise. Okay? So the users of that enterprise are the only ones who can request resources from that cloud. Okay? So think about, let's say UMass wants to build its own cloud. So it could build a data center and have servers and allow you to lease resources as research students or research staff. Okay? But this cloud is not open to anyone else. It's closed and is only available to individual users or groups within that enterprise. Okay? So that's called a private cloud. Okay? The advantage of a private cloud is the company now has more control over the servers. They know that the data is now more in their control because there are all kinds of legal regulations you have to follow. When you have data, if you're a bank, you just don't go and put your customer's credit card data on some servers, because if there is a breach, then you are liable for it. So you have to protect data in many different ways. So in this case, this is the way you are actually going to use cloud functionality or benefits of cloud, but not have to go to a completely open cloud. Okay, you create what is called a private cloud. Okay, so you use cloud computing concepts in a private data center that the enterprise is going to own, but it does all of that. It automates the VM management, deployment. You can go and request VMs and so on. Cost may be a little higher because you don't get the economies of scale. Your data center is not going to be as big as Amazon's data center because they have 10,000 enterprises using them. You are one enterprise, so your data center will be smaller, but it will give you all of the other benefits, okay, except for the economy of scale benefit. That's called a private cloud. Okay, large companies have their own internal clouds, which are private clouds. Okay, but many companies also use public cloud resources. Okay? And the hybrid cloud, as the name suggests, essentially combines resources from a private cloud and a public cloud. If you have some of your applications running on a private cloud, some applications running on a public cloud, those collection of those resources across both is referred to as a hybrid cloud. It is a public cloud and a private cloud combined in some manner. Right? And the way, the reason enterprises actually need to make a hybrid cloud in some cases is you deploy a private cloud. Okay? You have your own data center. Maybe you bought 10,000 servers, you put them there. At some point, you might say, I'm running out of capacity. Okay? So if you are just using private cloud, you have to go buy servers and it will take a few weeks to arrive and deploy. But if you could just go to a public cloud and just for a period of time say, I need 100 servers because I am 100 servers short, you can just get them and deploy them for some application. Maybe the less mission critical ones where you don't have to put lots of sensitive data on a public cloud platform, but the less sensitive things you can still run on those servers. So in this case, you combine resources from a public cloud and a private cloud to meet an enterprise's needs. Okay? And when the extra demand goes away, you can relinquish the servers and go back to using only your private cloud. Okay? So many large companies actually do this. Okay? They will have their private cloud, but it is sized, or the size of that cloud or data center is designed for some workload in mind. And if the workload capacity goes up, then you might have to temporarily overflow into a public cloud and then get resources there. Right? So this, if you do this, it's called hybrid cloud. Right? And there's software to move data back and forth that you can deploy. That's called hybrid cloud software and so on. Yes, question there? Okay, your question is a combination of servers on a public cloud, servers on a private cloud and storage in a public cloud be considered a hybrid cloud? Is that your question? So that's a form of hybrid cloud. Okay? Typically, you will do the opposite, just to be clear. You want to keep your data in your private cloud because data has to be more secure, and the compute might be elsewhere that might be remotely accessing the data. That way, the data never leaves your enterprise premises and it can be secured. If once you put data somewhere else, you got to secure it further. It doesn't mean it's not secure, but you have to take extra steps to secure it. Okay? So that's, but yes, what you said is also a hybrid.
Where does the Unity computing cluster fall?
Okay. Question is, where does the Unity computing cluster fall? So the Unity cluster, for those of you who know, Unity is UMass's GPU and CPU cluster. Okay? So you're doing research that requires you to do things like ML training or any of these large workloads. You go get an account on Unity and you deploy them. Okay? So as it turns out, Unity is not a cloud at all. It's a cluster. Okay? It is essentially it uses a distributed scheduler, which we talked about 3 or 4 classes ago. Remember, I talked about Slurm and so on. So in Unity, you get an account, you basically submit jobs, and the scheduler is going to then take your job and put it on some servers and send it back. Okay? So it's only going to run batch applications. You're not renting servers. Okay? Neither do you have any control over which job runs on which server. The scheduler decides it. Okay? In this case, you actually go and rent servers. So they are your servers until you rent them, you can log in and do whatever you want with them. So Unity is not a cloud. Okay? Unity is a compute cluster that provides computing services to end users. Okay? So it's not really a cloud in that regard. Okay. All right. So with that, I just want to talk a little bit about cloud workloads, then we'll talk about Kubernetes. Okay, so we talked about all kinds of cloud flavors, infrastructure as a service, platform as a service, software as a service. So all kinds of workloads are run on them these days. The most common one that actually made clouds popular were to run web application, web services on them. You deployed websites and web applications. Okay, so they ran on these cloud services. You could rent servers and then run them. Then they became popular for doing batch processing applications, things like data processing, ML training is now. A lot of machine learning training happens in the cloud. Okay? The reason is GPUs are very hard to buy. Okay? There's no capacity. There's always out of stock. But these cloud providers already have tens of thousands of GPUs available for rent. So you can just go rent these GPU machines, upload your data, run your whatever PyTorch, TensorFlow training, and get the model, and then you give back the machine, and you only pay for that time rather than buying very expensive GPU servers. Right? So that's batch processing and data processing. Okay? And I already mentioned ML training. So these require you to get cloud servers specifically with GPU. There are all other kinds of scientific applications in domains like physics and astronomy and chemistry and medicine. They have large data sets. They use them to run simulations or do other data processing. All of these tend to be good use cases for cloud services. And so this has now become a very popular model for running large-scale compute. Don't buy, instead rent. And if your workload is not going to run for years at a time, it's always cheaper to rent. That's the general idea. Any questions here? Okay. I'll say, okay, there is actually one more slide here before we go to orchestration, which is storage. I didn't actually talk much about it. But so cloud platforms also offer storage. Okay? This is something all of you are actually using and are familiar with. Right? So in this case, the cloud platform provides you storage space that you can use. Okay? Google Drive, the example of cloud storage. OneDrive, an example of cloud storage. Right? iCloud, an example of cloud storage. So in this case, you are renting disk capacity from the cloud. You're not renting servers. You're not renting platforms to run code, but you're renting storage space. Okay? And as a monthly charge. Okay? In case of university Google Drive, university is paying your charge. But if you actually had, like if you have iCloud, you can pay for some amount of storage. There's a charge per month that you have to pay. Right? So you pay a monthly fee. You get some amount of disk space. You can use it to put your photos or documents and whatnot. And then you can access it from any machine. Okay? The reason it's useful is once you put things in the cloud, you can then log in with your credential and access it from other machines. So it's much more flexible than if you kept all your data on your local machine, then you go somewhere without your machine, your data is not accessible. So this makes it accessible from multiple servers, multiple clients, and so on. Okay? So that's an advantage of cloud storage. Okay? So Dropbox, Google Drive, OneDrive, Box, all of these are services that provide you cloud storage. There are many others as well. Okay? But there are many ways you can also get this storage. The typical one is file storage. This is what Dropbox and Google Drive provides you. Essentially, you can create files, you can create presentations using Google Drive or OneDrive and so on. So it gives you file storage capacity. Okay? But there are also other types of cloud storage that give you block storage or object storage, where you get larger amounts of storage. Okay? You can essentially, you don't create files on them, you create blobs of data, which are just arbitrary chunks of data, and you use methods called get and pull to essentially get blocks or put blocks. Okay? So in this, the way this object storage techniques work is that you can ask for, let's say, 1 terabyte of object store, and you'll get 1 terabyte of space. You are not going to create files and directories in them. Okay? But you can put large amounts of data and retrieve them. Each chunk of data you put in gets you a handle. Okay? The handle is the identifier. So there's no file name. Now in file system, the file name is your handle. In this case, you will get a numeric identifier. There's a handle for that. And then you want to retrieve it, you have to present the handle and it will give you back the data. Okay? So you can use this to create storage for large amounts of data. You use it to create archives and so on. It's a very different way of using disk, of using cloud storage from your standard disk and file model that you are very familiar with. So you don't use, in this case, the cloud storage in that format. You use it to store what are called objects, okay, rather than files. But beyond that, the concept is the same. Okay? You're going to rent some storage space, but instead of putting files, you're putting objects. And you can do gets and puts on those objects to retrieve them or store them back. Okay? So in any case, that's all I have for cloud computing. If there's questions, this is the time to ask before I move on to the next part, which is cloud orchestration and Kubernetes. Okay. All right, so let me explain what does orchestration mean first, and then we'll talk about one way to do it using Kubernetes. Okay. So as you might have realized, okay, all of these cloud platforms have some sort of a control node. Okay. When a user goes and says, give me a small server, small virtual machine, okay, some piece of software that's running in the cloud has to figure out which of the physical servers has enough capacity so you can create a virtual machine and allocate it to that customer that just asked for a new virtual machine. Okay. So there's some control software that keeps track of what are the servers in the cloud platform, which servers are in use, how much capacity has been allocated, how much capacity has been freed, where to put new virtual machines, how to resize them. Okay. So all of this management functionality is called orchestration. Okay. So this is essentially the cloud software that is going to decide how to allocate resources to end users, okay, or how to move these virtual machines around if resources get overloaded and so on. Okay. So this is called a cloud controller, which we have not really encountered, but that's the thing that's actually doing all of the work to make it simple for you. Okay. So all infrastructure as a service platform as well as other platforms, the PaaS and IaaS, have a cloud orchestrator or a controller that's doing all of the work. Okay. So now what we will see is one specific one called Kubernetes, which is an open source orchestration framework that's very similar to what you will see in a real cloud platform. In fact, Kubernetes is actually something that Google developed. Okay. It was based on their Borg and Omega cloud controller or cluster manager. We already encountered Borg when we were talking about distributed scheduling. Remember I said this is the scheduler that Google uses to schedule all workloads in the data center. So it was a cloud orchestrator. I didn't use that term there, but it's doing orchestration. Okay. They open source parts of Borg and they made it Kubernetes. So essentially you can use Kubernetes to create your own cloud. Okay. And then you can go to the Kubernetes cloud cluster manager or in this controller and say, give me some resources. Here it's going to use containers. It's not going to use VMs. Kubernetes is a container-based manager. So it will create a container of a certain size and hand it to you and so on. Okay. So everything we are talking about, you can essentially do that orchestration. In this case, we'll use Kubernetes to do this. But the thing you want to keep in mind is this is derived directly from Google's actual schedulers in their data centers. They made it open source. You can now download it and run it on any machine. There's going to be a lablet on Kubernetes so you can actually play with it. Okay, so you can figure out how to use it. So what are the things it will do? Okay? You can basically deploy an application onto a cluster of machines. It will figure out which machines have enough resources, and it will deploy your containerized application. In this case, they're not VM based, they're container based on this application. It will automatically replicate them if you want to. It provides this service so that if some machine goes down, you have a second replica running. It will do that. It will load balance. If you create replicas, it will send your requests across machines. It can scale these containers up or down. If the workload goes up, it can scale it up or down. It can provide automated restart if there's failure, self-healing, and so on. So it provides lots of services that are built in. So as a developer, you might not need to worry about lots of these things. Saying you don't have to worry about what happens if the machine fails. Kubernetes cluster manager or the orchestrator in this case will track it and restart your application on another node, okay? And then redirect requests there. Or if the application gets overloaded, it will resize it on the fly. you have multiple replicas, you replicated it, load balances them. Okay. Lots of useful services. Okay. We'll come back to some of this when we talk about the web, okay, and we talk about web-based application. But as of now, you just need to understand at a high level what is actually happening. Okay. So let's get into the details of how Kubernetes works. And by the way, it's called, the acronym is K8s. Okay, that's what you will see. So when you see K8s, they essentially mean Kubernetes because they don't want to spell the whole thing. Right? So this acronym is called K8. Okay. So the way this works, okay, is the granularity of resource allocation in Kubernetes is called a pod. Okay. A pod is like, think of it, it's not unlike a virtual machine. It's a slice of a server. Okay. So here's a machine. Okay. Host A, that's a physical machine. Okay. This machine essentially has a single pod at this point. Okay. That's this gray box in there. Okay. That's a slice of that server that you allocated to that application. Okay. That application in this case has chosen to run 2 containers inside this pod. Okay. You can run 1, you can run 10. That's up to the application. So application goes and requests some amount of resources. Those are allocated as pods. Okay. You can have more than 1 pod. Each pod runs on the machine. But the simplest thing is you ask for something, you get 1 pod on 1 machine. Okay. Your application is distributed, you might get more than 1 pod. Okay. And then it's up to the end user to say, okay, each pod is going to run my code inside a container. Let's say it's a Docker container. It will basically run that in the code. In this case, we've shown 2 containers, but you can just run 1. That's the simplest case. 1 pod, 1 container. Okay. But in this case, you have 2 pods. Okay. And you can have more than this on other machines. Okay. So distributed applications have multiple components. In the Kubernetes world, you have to take each component and put it inside a container. Okay. If you have 3 components, you will create 3 containers. Component 1, container 2, and 3. Okay. And then you go as a user and go and request 1 or more pods from Kubernetes. And then you say, deploy my containers inside that pod. The simplest thing is, in this case, you ask for 1 pod and you'll take all 3 containers and put them. So these are the 3 components, and then they work together. Okay. But you could have asked for 3 pods and each container goes in 1 pod. Okay. Then your application automatically running on 3 different machines if the pods are on 3 different machines. Okay. So you can distribute them that way. Okay. So the pod essentially can contain all the containers of an application, but if you want to scale it up and down, it's better to put each component in a separate pod, and then Kubernetes will scale it up or down for you. Okay. It can essentially make the container bigger, or it can deploy a second application, a second container to scale it and so on, because it has auto scaling built into it. Okay. So a lot of this are very advanced functionalities, some of which we're encountering for the first time, but we'll talk about auto scaling as well. But all you need to know at this point is this is a way you can deploy containerized applications, okay, using a cloud-like framework. So it looks exactly like a cloud where you have to go to the Kubernetes manager and say, give me a pod. Instead of asking for a virtual server, you ask for a pod. Then you deploy your application in a container on that pod instead of deploying it into virtual machine. Equivalent things in the container world. Okay. It's a very popular way to deploy applications in the cloud. Okay. So there are 2 terms I want to mention here. One is called a service. I already mentioned the pod. Okay. Pod is essentially a slice of a server. So here your pod on machine A, your pod on machine B. Each of them is running these blue things are containers that are running there. So you will see that there are 3 here and 3 here. There are 6 containers for this application. Okay. Now, when requests come in, you have to decide how do requests get to those containers. Okay. To do this, you are going to have another component called a service. Okay. The service is like the load balancer. So requests actually come to the service. The service will then forward them to containers. That's an internal decision, okay, that you make. So the service is the method you are going to essentially access pods, expose interfaces. So the service has a static IP address. You can make that visible. So if you have a web service, or web application rather, you will make a Kubernetes service, and whatever IP address this service gets is what you expose. So your web browser will connect to this component, send its request here, and this component will forward it to one of these containers to actually service the request. Okay? That's the way it's going to work. So the containers themselves are not directly exposed outside in this world. Okay, this is like a load balancer, or it's a more permanent component that's going to expose them. The reason this is good is if this entire machine fails, okay, Kubernetes will track that. It will know that there are 3 containers running. It will allocate a pod automatically on another machine. It will restart those containers there. It will tell the service that there's all the containers are moved to a new host, and then the service will start sending requests there. It's all transparent to the end user, okay, because it has all this built-in failure management capabilities in there. So pods are ephemeral, which means they're temporary. That's why you don't expose them. They're only seen by the service. Services are actually more permanent, and that's what you expose. So this is the Kubernetes way of deploying application. Okay? They have decoupled the machines that are running the code from what is actually exposed to the end user. Okay? What is exposed to the end user is this concept of a service, which is just another piece of code, but it has an IP address that you're exposing to end user, and then that service is the one that forwards requests to containers in pods. Is this clear? This is a Kubernetes model. So this is how you will actually build. If you want to deploy, let's say build a Docker application and you want to deploy it in a Kubernetes world, your Docker container is actually going to be that. Okay? But you have to have an additional component called a service that you have to also build, that you expose it, and that service is the one that will actually send requests to your Docker container. Is that clear? Okay, can a component run in multiple containers? As I said, Kubernetes allows replication. So in fact, you will see that this prod service is actually running in 3 containers here, right? This MySQL, there are actually 2 containers here. So this is already replicated. So yes, they can run in multiple containers, and the service knows about them, and it can load balance across them. The question is, does it have to be done by users, or Kubernetes does it automatically? The user has to specify if a container should be replicated or not, and how much it should be replicated. So you can say this container should have between 3 to 10 replicas, and then it will figure out it should be 3, 7, or 10. Or you can say only 1, in which case it will start only 1. Once you specify that, it's the Kubernetes job to figure out where to run them and so on. It will allocate these pods, it will deploy them and so on. Right? So it's automating that. Yes. Yes. The question is the pod running in data centers, and Kubernetes is a way to orchestrate that. Yes, that is indeed the case. So you can run them in a data center. You can actually, because it's open source, you can run it on 2 laptops, and you can create a Kubernetes cluster, and it'll give you the same functionality as if you went to a cloud and did the same thing. But yes, technically you will not run this on laptops. You'll run them on servers in a data center. It's doing orchestration, right? The cloud has similar orchestration for virtual machines. I'm just showing an example of an open source orchestrator that's doing containerized deployment as opposed to virtual machine deployment. Okay. The last thing is the internals of Kubernetes. You will see that there are some similarities between this and the Borg model, because this was derived from the Borg model, right? So essentially there is a API server which allows clients to come and say, give me a pod, I need so many containers. So this is the API that Kubernetes exposes to users of the cluster. So you can go and request resources, very similar to how you go to cloud and request resources. Okay? etcd is the key value store. So this is the database that's going to keep track of what are the physical servers, how many pods are allocated on them, how many resources are free. So this is tracking all of the resource allocated on the cloud. And just as in Borg, this has to be is replicated on multiple machines, and it uses consensus to keep them all in sync. And if one of them goes down, there is still some other machine that has the state, because once you lose the state, you cannot do any allocation. So this has to be, you have to make sure it doesn't go down. And then you have several other components like controller manager that's going to do replication or check for failure. The scheduler says, I'm going to allocate newly allocated pods to users and servers. Okay? And there is a cloud control manager that can actually take this and work with other cloud platforms and so on. Okay? So lots of components, but at a very high level, this is similar. This orchestrator is really similar to Borg because it derived its thing from Borg. So there's an interface exposed to end user. There's a database that keeps track of what the cluster looks like at any given point in time, and then a set of components that do resource allocation. Okay? So these are by and large what is shown here. Okay? And then at the very bottom, just as you had a Borg LED, you have something called a kubelet. Right? These are essentially machines that are running pods and so on. Okay? Any questions on this? Is a very high level thing, but you will get to play with this a little bit in your lablet, so you get some flavor of it. You may not know the internal details, but that's not completely needed. It's better to know how to use it to deploy applications and so on. It's just a high level understanding of the internal. Any questions here before we wrap up for the day? Okay, so we will stop it here, and next time we'll start a new topic. So we are done with cloud, virtualization, all of this. We are going to switch gears and start a completely new topic next time.